Good morning. It's time for another one of these daily coding problems. These usually come from dailycodingproblem.com or the LeetCode interview question list. Most of these questions are asked by tech companies, and most of the time that company is indicated. So let's look at the question for today. This problem was asked by Google. I got my stopwatch going. We've got up to half an hour to finish this. And yeah, these are lots of fun. These aren't necessarily related to programming in the real life. They're usually just little fun puzzles. So let's see what this one has in store for us today. Implement locking in a binary tree. A binary tree node can be locked or unlocked only if all of its descendants or ancestors are not locked. Design a binary tree node class with the following methods. Is locked, which returns true if the node is locked. Lock, which attempts to lock the node. If it cannot be locked, then it should return false. Otherwise, it should lock it and return true. Unlock, it unlocks the node. If it cannot be unlocked, then it should return false. Otherwise, it should unlock and return true. You may augment the node to add parent pointers or any other property you would like. You may assume the class is used in a single-threaded program, so there is no need for actual locks or mutexes. Each method should run in O of h time, where h is the height of the tree. Sweet. Okay, so we're building a tree, and I'm thinking we're going to use recursion for this, and if we use recursion, then our runtime should be okay, right? Because we'll just, when we want to unlock or lock a node, we'll just walk all the way up the tree to the root to check the ancestors and make sure that those are all unlocked. And then we'll also walk down the left and the right tree as well to make sure both of those are unlocked. And I think it says if all of its descendants or ancestors are not locked. It doesn't say and, right? So we really only need this to be unlocked or this to be unlocked, but we don't necessarily need both to be unlocked. I think that's all we need, right? Okay, let's get cracking. Usually we use like a solution test is what we call it, but let's just create these tree nodes. And so we'll create a tree node test, and we'll use mini test for this, and mini test pride so we get colors, and then we need to include our tree node as well, which is what we want to test. And then let's describe what we want the tree node to look like. We've got three, I believe three, right? Is lock, lock, and unlock? Yeah. Okay, we've got three methods we want. So let's do lock. And then unlock. And then we also, you know what? Instead of calling this is locked, I'm just gonna go locked like that. Make it a little bit more Ruby-y. Let's put this one at the top. Okay, so let's start with locked since that's going to be the easiest one. It returns true when the node is locked. It returns false when the node is unlocked. And I'm just thinking to myself here, it's going to take us a while to write these tests, right? So what I'm thinking about doing is just creating one tree that we can use in all these tests. And then we can just lock and unlock nodes as necessary for the different cases. So I'm going to build that tree up top here. So our tree, let's draw a little tree here. So we're going to have a root, and we want to give it some depth. Other bracket, there we go. So let's add a left. How about L child? L child 1. And for short, I'm going to call that LC1. And then RC1. And 1 is kind of the depth, I guess. And then let's give these some children as well. And then this will have LC2, LC, oh gosh, what are we going to call this? So we got left child 1, right child 1, left child 2, left right child 2. Guess we're going to have to insert some spaces in here. There we go. And then right left child 2, right child 2. Wow. Whew, okay. That's a disaster. Okay, so this is going to give us enough layers, I think, that will satisfy our test. It's tall enough. Let's remove a bunch of these spaces now, and then we'll build this tree in code, and then that should make writing our test quite a bit easier. So let's create these nodes. We're going to have a root, which is going to be a tree node. And do we need anything inside this tree node? I guess we can default all our tree nodes to being not locked. How about that? So how many nodes do we have? 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay. So now we've also got an LC1 and an RC1. And then we've got a left LC2, left right C2, and then a right left C2, and a right C2. Perfect. So those are all our nodes that we can use in our tests. Now let's actually build the tree here. This is where we'll take all our nodes and assemble them. So we'll start with our root, and the left is going to be LC1. And the right is going to be RC1. Okay, great. Now let's go down a layer. So now we have LC1. So LC1, now our README said that we can assign parents, right? And this is going to be useful when we're checking ancestors. We're going to want to walk all the way up the tree. So let's set that. So we have LC1 parent is equal to root. And then we'll set the children as well. LC1 left equals LLC2, LC1 right, and I'll put a space in here, equals LRC2. Perfect. Now we'll do the same for our right side, which is RC1. RC1.parent is the root. So that's going to be RLC2 and RRC2. Perfect. Okay, now we've only got these last 4 nodes here. 1, 2, 3, 4. So we've got LLC2.parent is equal to LC1. LRC2.parent is equal to LC1. And I'll put those right there. And then we have RLC2.parent is equal to RC1. And our last child, RRC2.parent, is equal to RC1. And those don't have any children. Whew, goodness. Okay, so we've got our tree assembled. Now, writing our test should be much more straightforward. So let's do this first test. It returns true when the node is locked. Perfect. So we can say root.locked equals true, and then assert root.locked. Let's run it. Okay, it can't find our tree node because we haven't created it, so let's do that. Okay, wrong number of arguments. Initialize, and we know we are passing in locked. And we'll default this to false, and then we'll save it. And then we'll make it writable. Well, actually, do we want to make this one writable? Yeah, we do, because we're going to use it in our tests. Perfect. Let's try again. Undefined method left equals. Okay, so now we know we're going to want left and right and parent as well, right? Those are all things we created. So let's do left, right, parent. And we'll add them here as well. Left, right, parent. Let's try again. Missing keyword arguments, left, right, parent. Oh, right. We don't want to require these. We want to have these be nil by default. These are not required. Undefined method locked. Perfect. So now we're at actual failure we care about here. So this is going to return true if it's locked, right? Let's make sure we get back what we're expecting. Expected nil to be truthy. So now we should be able to just return locked. Great. Okay, so that test passes. Let's move on to our next one. Returns false when the node is unlocked. So now we can just set lock to false and then refute that. Run it again. Great, that still passes. Let's move on to our next test. So now we're going to start doing the tree traversal stuff with our lock and unlock. So let's use our existing tree to do that. We've got basically 4 scenarios we want to test, right? We want to test that it locks when all the ancestors are unlocked. We want to test that it locks when when any of the ancestors are locked. And then we want to do the same for descendants. We want to make sure that it locks when all of the descendants are unlocked. And we want to test that it does not lock if any of the descendants are locked. And then we can copy and paste those test cases for unlock. So it should be quite a bit faster once we have this part working. So it locks when all ancestors are unlocked. It locks when all descendants are unlocked. It does not lock when any descendant. It does not lock when any descendant is locked. And it does not lock when any ancestor is locked. Okay, so there's our 4 test cases. Let's start with the first one. Locks when all ancestors are unlocked. So we already know that all our nodes are unlocked, right? So let's not even worry about setting up any state here. We should be able to do root.lock and then assert. We want to make sure that returns true. And then let's also just go ahead and do assert root.unlocked. Or no, assert root.locked is what we want, right? Okay, so let's give this a shot. Undefined method lock, perfect. That's what we expected. Let's create it. Expected nil to be truthy. So let's do, let's return true. Run it again. Expected false to be truthy. So now it's testing our locked method here. So now we can do locked equals true, and then let's return this. Okay, So our first test passes. Let's move on to the next one. Locks when all descendants are unlocked. Okay. This is basically the same as this one, right? Oh no. So this is all when all ancestors. Oh, okay. Actually, so a root doesn't have any ancestors, does it? So let's move our root here, and this is gonna check all the descendants. And now for our ancestors test, let's pick a node that has a bunch of ancestors. So like this one here, LLC2. So now we'll use LLC2. And this is gonna test that when LC1 and root are unlocked, that we can lock our node. So let's try running this test. Great. It should still pass, right? We haven't changed anything. These tests will be useful, I think, when we start writing this, because it's going to make sure we don't break anything. So now let's do our first test where we need to do some lock checking. So does not locked when any ancestor is locked. So we'll go ahead and use LLC2 again. So we're at the bottom of our tree. And now our state here is we want to lock an ancestor. So let's lock the topmost ancestor so we can check that we're walking all the way up the tree. So let's lock the root. So root.locked equals true. And now we should refute that we can lock this, and we should refute that the node is locked. Let's see what happens when we do this. Okay, we still got true, as we expected, right? We haven't written any code here yet. So let's open up our class here, and now we're gonna have to start writing our recursive bits. So this is checking for ancestor, right? Does not lock when any ancestor. Okay, so now let's do this. If ancestors are unlocked, so we'll just add this to our lock method. If the ancestors are unlocked, then we can lock it. And now if we run this, it's gonna tell us we don't have ancestors unlocked method, because we don't. So we're gonna make this protected, and then let's go ahead and do ancestors unlocked. And what does this look like? This is where we're gonna use that parent connection that we have. So if we have a parent, and we might clean up these if statements in a second here. So if we have a parent, then we do some stuff. If we don't have a parent, then ancestors are unlocked, right? So if we have a parent, then all our ancestors are unlocked if our parent of this node is unlocked and the ancestors of the parent are unlocked. So this is that recursive bit here. So this is gonna call ancestors unlocked and keep walking up the tree. So let's run this. I don't think we've defined an unlocked method yet, right? So let's run this. Yeah, undefined method unlocked. So let's create that now. And this is going to be not locked. Let's run this. Okay, so that works. So let's see if we can clean up this if statement a little bit, because this looks a little garbagey to me. So ancestors, so this is gonna be not parent or this. Okay, let's run it again. Excellent. Okay, so we've got that bit done. Let's go ahead and do does not lock when any of the descendants are locked. So we'll pass in our root again, but let's go ahead and lock, like, say, this node down here. So this is RLC2. RLC2.locked is equal to true. And now we want to refute that that node can be locked. And then, of course, we want to refute that it's locked. Okay, let's give this a shot. It fails, as expected. Because all we're checking now is the ancestors, so let's go ahead and check the descendants now too. So if ancestors are unlocked and our descendants are unlocked, then we'll go ahead and lock it. So now we need to say what descendants unlocked looks like. Now this is going to be pretty much the same as what we've got for ancestors, except we need to check both the left side of the tree and the right side of the tree under the current node, right? So what does that look like? Let's start again with our if statements, then maybe we can shorten it up in a second. So if left, right, and let's call this left unlocked. So if we have a left node, then we need to do some stuff. If we don't have a left node, then the left is unlocked, right? And what do we actually want to do here? So the left is unlocked if the left node is unlocked and the left descendants are unlocked. Okay, so it really is just like what we had up here. So we can do not left or that. Okay, so now we've just checked if our left is unlocked. If our left is unlocked, then now we can check the right-hand side. There's no point, if the left isn't unlocked, then there's no point in checking the right-hand side, right? So if left is unlocked, then now we can do the same thing on the right. If the left isn't unlocked, then we return false, right? So we check the left-hand side. If it's unlocked, then we'll check the right-hand side. Otherwise, we return false. So let's run our tests again. Outstanding. That worked. Okay, so now we need to do unlock, which is almost exactly the same. So we're going to take our same tests and copy them here, change the wording here. It unlocks when all ancestors are unlocked. It unlocks when all descendants are unlocked. It does not unlock when any ancestor is locked. It does not unlock when any descendant is locked. And now let's rewrite these to use unlock. So we'll add a couple asserts for unlocking there. Then now here we're going to unlock the root node. Does not unlock when any ancestor is locked. So this is the same. And then this is the same. This is when any descendants. Okay, let's run this. Bunch of failures because we don't have a method called unlock. So there we go. And boy, this is going to be real similar, isn't it? So if our ancestors are unlocked and our descendants are unlocked, then we can unlock this node. And then we want to return not if it's unlocked, or not if it's locked, but if it's unlocked, right? Okay, let's try this. Uh-oh. Does not unlock when any ancestor is locked. Oh, our test is a little messed up, isn't it? So does not unlock when any ancestor is locked. So with this one, let's try. So I just realized something too, right? It only makes sense to unlock a node if that node is locked. So let's do llc2.locked equals true, and then we try unlocking it, right? Okay, so let's do that for each of these. So we want to lock our root node, and then unlock it. And then in this case, we want to lock both the node at the bottom of our tree and at the top and check that it can't be unlocked, right? Okay, great. And then finally, our root node needs to be locked in this test. And then we want to verify that it cannot be unlocked. Okay, all our tests are running. I think we're good to go. Let's go ahead and see if there's any code we want to clean up in here. This looks pretty good to me. Let's toss this in a commit. Here's our tree node. And our tests. Add solution for today, which is the 25th of February. Okay. Another good one today. We've had, I think, 3 in a row now where we've just solved with recursion. So we'll see if we have something different for tomorrow. And I think we've written that tree node class 6 different times now, looking back at all the times that we've done this. So definitely seeing some patterns here. Google, Facebook, Uber, they've all asked these kind of tree questions. Anyways, thanks for tuning in. We'll see you next time. Bye.